Next up, our next presenter is Lachlan Sneff of Pennsylvania State University, presenting one of my favorite titles so far this week, Rocket-Powered Crabs. So Michael, if you can go ahead and stop sharing your screen and we'll begin sharing. There we go. And Lachlan, see you coming on, and
hey.
We see you just fine. And
Awesome.
We hear you just fine too.
Excellent.
All yours.
Excellent. So hey everyone, I'm Lachlan Sneff, as you can see. I'm an engineering science student at the Pennsylvania State University, which is in Pennsylvania, as you might guess. And I'm also the avionics electronics lead for Penn State's student liquid rocketry team, which is called SEDS PSU Liquids. I want to thank the Flight Software Workshop organizers for giving me this opportunity. And I'm really excited about telling you guys all about what we've been working, what the student team has been working on. And I hope you all find it really interesting. So the elephant in the room, the title of this talk, what does it mean? So this whole project, at least the avionics part of it, was in a large part enabled by the Rust programming language. And I'll talk more about why that is later on. And as you may or may not know, Rust's mascot, and a programming language with a mascot, yes, is a crab named Ferris. Therefore, the title and title imagery of this talk. Next slide, please. So this talk has two goals. First, I'm going to show off what my university's rocketry club is working on and also how I'm involved. And then I'm also going to spend a bit of time talking about Rust in this context, in aerospace and in the context of this particular project. Next slide, please. And before I get too far into it, I need to give you all some context. So SEDS PSU is the Penn State University chapter of an international organization called SEDS, which stands for Students for the Exploration and Development of Space. The goal of SEDS PSU Liquids, which is a sub-org within this PSU, within the SEDS PSU organization, is to design and build, and we're all students in the club. First, a bipropellant rocket engine, and then second, a rocket around that engine, so we can compete in the 2023 Spaceport America Cup. My group within that group, called SEDS PSU Liquids Avionics Electronics, it is quite a mouthful. We've talked about coming up with some acronyms. Is focused on designing the electronics and flight software necessary to test fire the engine this semester. So far, we're well on track for the scheduled half-second test fire in late April. Next slide, please. As I said before, SEDS PSU is a chapter of the overarching SEDS organization. SEDS PSU itself has 3 child teams within it: SEDS Liquids, SEDS Solids, and SEDS USLI. The SEDS Solids and SEDS USLI go off and compete in other challenges and both work on solid rockets. SEDS Liquids in of itself is all about students designing and building a liquid rocket engine. And we've organized into several sub teams, which are structures, propulsion, fluids, engine, and avionics. And then avionics is a further child sub team called electronics, which I'm the lead for. And the team is effectively the 3 of us, Rio, myself, and Nicholas, though we have had a few other members join very recently. Next slide, please. So we're building a frickin' liquid rocket engine. That is so damn cool. The engine is run with nitrous oxide as the oxidizer and ethanol as the fuel. It's pressure fed, which is the simplest way of building a liquid rocket engine like this. I know there are some student teams who have built turbo pump fed rocket engines, but we're not at that point yet. The nozzle is ablative graphite, so effectively it cools down by pieces of it breaking off. And it's ignited by essentially an Estes rocket motor, just an off-the-shelf solid rocket motor, which burns for just a few seconds and is ignited just before we let fuel into the chamber. Next slide, please. So there's a lot going on here, actually, at least in comparison to the kind of stuff we've done before. The avionics, which is on the test stand itself, so right next to the rocket engine, it routes the ethanol, the nitrous oxide, and nitrogen through the fluid system using 12 solenoid valves. And there's also a bunch of manual ones, which are used during the filling process. There are also like 20 different sensors. I think it's 20 now. Of 4 types that are all read at 100 hertz. And they're stored on the test stand as well as on the ground station. Next slide, please. Yeah, there we go. Yeah, so this is how we're going to get the whole setup from our lab to the testing site a few miles away. I'm really not kidding. We do have to take the rocket engine itself off of the trailer during the drive over, unfortunately. Next slide, please. We designed 3 different boards for the avionics system. 2 of them have microcontrollers on them, which is an STM32F105, if you're curious. We had a lot of trouble with sourcing these. The chip shortage made this a lot more difficult than it had to be, especially near the end of last semester. And the 3rd board is an extension hat for a Raspberry Pi. So just like an embedded Linux board. The output board just controls all the solenoid valves as well as the igniter itself. The sensor board reads all the sensors and sends the data to the Raspberry Pi, and then the hat itself just adds CAN bus support to the Raspberry Pi as well as a voltage regulator, which then powers the 2 other boards. Next slide, please. Here's how they all connect together. As you may note, the ground station is just a laptop, someone's laptop, connected to the test stand with a very, very long 100-meter, so 330 feet Ethernet cable, which is the maximum standard length of an Ethernet cable. For the actual rocket in 2023, we're going to use an even longer Ethernet cable, so like 10,000 feet. The 3 separate boards all communicate over a CAN bus, each one operating as a single device on the CAN bus, so with a single ID. And then every 10 milliseconds, the Raspberry Pi asks the sensor board for the current sensor data, and then asks the output board for the current valve states, so it can check that things are on track. The way the output board knows what valve states are is just, it kind of guesses like what the current state is, because it actually doesn't have feedback as to what the real states of the valves are, aside from what it set them to, and then aside from like associated like changes in pressure or stuff like that. So next I'm going to talk about each board more in depth. So next slide, please. Cool. So all the hat does is add a CAN bus controller and a voltage regulator to step the battery voltage down to 5 volts. On the other boards, the 5 volts is then stepped down to 3.3 for the microcontroller. And then the Raspberry Pi itself, which runs underneath this, just does 2 things. First, it talks to the ground station laptop over a WebSocket connection. And then, as I mentioned before, it just communicates with the other 2 boards over the CAN bus. The Raspberry Pi itself runs a Linux distro with the real-time patch, and the threads are pinned to specific cores and all that, so we can guarantee like a certain amount of latency. We didn't need hard real-time for the Raspberry Pi, since all of the stuff that needs around 1 millisecond or less of timing accuracy runs on the other 2 boards, and those have no operating systems, just kind of bare metal, so they have like very, very hard real-time. During next slide, please. During the normal operations, the output board receives a status request from the Pi every 10 milliseconds, as I mentioned before. But when the engine needs to be fired or fueling needs to take place, it actually receives a list of commands from the Raspberry Pi itself. Instead of the Raspberry Pi sending out like 1 command at a time, like set all the valves to this state, and then at some point in the future would send like ignite or something like that. Instead, we send all of the commands at once with kind of delay values between them, so we don't need to worry about timing issues on the Raspberry Pi, because it isn't like real time. It's still running Linux, even though it is Linux with the real-time patch. And I'll talk more about these commands in a sec. But they are things like just like set all the valves to these states or fire the engine igniter. So this thing you can see here is like a request. And I want to point out, because of Rust's really excellent meta programming support through macros and stuff like that, we can do things like declare this structure and this enumeration, and then have it serialized and deserialized really compactly and safely as it's sent between different devices, so that it's kind of like code as specification for the communication protocols. We don't need an external specification or external documents. All of the format specification is actually just the code, and actually this is the structure that's used in the code for the different devices. Next slide, please. Each command, as I mentioned before, has like a wait or delay in it. For example, the half-second test fire would consist of like setting the valves to closed positions. This would be a list of commands. So set all the valves to closed positions, and then firing the igniter, and then waiting a short time, and then having a delay after the ignite, where once the hardware detects that the igniter has actually fired, it then waits a certain amount of time before going to the next command. And the next command would be setting all the valves so that fuel and oxidizer flow into the engine chamber. And then there would be another wait of half a second, and then setting all the valves to close. And this would be a single block of commands sent all at once to the output board, which are then executed over time. The output board, receives this list of commands and then executes them, and then it schedules each next command to be run in the future through a task system built on timers and interrupts. And remember, there's no operating system, no threads, none of that. It's all just no RTOS, even just kind of bare metal Rust. And then another thing I want to point out, which actually I'm quite proud of us thinking of, is that the output board, it needs to be fully powered up during the fueling process, because there are valve changes that need to be run during the fueling process that can't just be manual. But then we also felt like it would have been dangerous to have the ignition and also the fuel lines, fuel and oxidizer lines going into the chamber itself, just be like kind of stopped from being activated just through software. We felt that was dangerous. So we actually added like an additional section of the PCB. It's in that kind of bottom right-hand corner where there's an additional MOSFET there that physically prevents the engine chamber valves and igniter from being activated unless an actual physical button at the ground station, or the ground station's laptops and next to the ground station, from when that's pressed. These can only be activated when that's pressed. So it's a very long cable, but we're proud of thinking of that because it kind of improves the safety of the system significantly. These PCBs are all have been manufactured and stuff, and they're just not in the slides. I guess this is a slightly older version of the deck, but it's fine. I'm happy to show them afterward if anyone is interested. Next slide, please. The sensor board reads all the connected sensors at 100 Hertz. And there are a whole bunch, different kinds, and they run in different ways. When the Raspberry Pi asks very nicely for the sensor data, it sends all the data back to the Raspberry Pi over the CAN bus. So the thermocouples are attached to the fuel and oxidizer tanks for temperature, as well as the engine chamber and a couple other things, are hooked up to an IC that's designed to read and calibrate the thermocouples. And that communicates with the microcontroller on the sensor board over I2C. And I had to write a driver for this because I couldn't find an existing one, but I think it should work fine. The pressure transducers and flow meters have a current output, which is then we have to, with a resistor, convert it to voltage and then amplify it through some high accuracy op amps. And then that's read by the onboard ADC. And then the load cells have a voltage output that's amplified and read by the onboard ADCs. So at this point, I'm going to switch away from the technical details, and talk more about what you might call meta strategy of how we decided to make this all work. Next slide, please. So the major goal I had when I joined the team in August, and one that I've maintained the importance of through this kind of entire adventure, was to learn as much as possible. And aside from actually getting the damn rocket to work, this is perhaps the most important thing, according to myself. So we're students. We have this opportunity now to make something that's beautiful, elegant, and functional before we have managers and funding agencies kind of breathing down our necks. And so kind of boiling all that down, let's make our own hardware from scratch. Let's use real electronics, real software. Let's do things, at least in part, how they're done in the real world. That being said, we shouldn't overcomplicate things any more than is healthy. A little overcomplication is a good thing in many cases. We didn't need wireless communication for this, for the test fire, so we just didn't do it. Instead of specialized hardware at the ground station, we'll just use Ethernet. And I didn't want to spend hours getting a network stack working on a bare metal microprocessor, so let's just use a Raspberry Pi for that part instead. This balance contributed to our decision to use Rust as well. We wouldn't have learned as much if we had used an Arduino or hobbyist hardware software platform like that. But I also knew from my experience that using C and an RTOS would have really overcomplicated the project. It would have taken a lot longer to get working, and it wouldn't have worked as well, at least from my experience. Also, the embedded hardware and software team is, at least for most of this, now it's a little different. Just in the last week or two, we've gotten an additional 1 or 2 people. But the embedded hardware and software team is basically 2 first-year students who are unexperienced with embedded software, and then myself. This really would have been an awful experience if we had spent the semester fighting with seg faults and data races, which from my experience with C, and those are very common. C++ would have been an option, but also I feel like C++, it's actually, you can't really officially use it on these bare metal platforms. This standard, I believe, requires an operating system. So with Rust, instead, you can run bare metal without an RTOS, without a bootloader. You still get all the niceties of modern development. You get a strong type system and a rich standard library. Though when you're running on an embedded device, you don't get any allocation or operating system stuff along with the standard library, just the core library as it's called in Rust. Actually, I think there was a talk earlier, I think yesterday, talking about Rust from Ada Core. And also looking forward, the whole embedded software industry is moving towards Rust. You in particular may not have felt the shifting sands yet, but it is happening, at least in large swaths of the industry. And I think this is going to become apparent over the next 10 years, maybe. And it makes sense. Rust has many characteristics that make it really excellent for embedded and flight software. Cool. On to the finishing remarks. Next slide, please. So this is a picture of most of the SEDS Liquids team. We're missing a few people here, and there are a few extra who seem to have made their way in, but it's about the right size. So it's not that many people. We have, I don't know, 15, 20 people, usually less when we meet. Next slide, please. And this is a picture of the SEDS Liquids leads. So in order from left to right, that's Ben and then myself. And then Matt, who is the lead of SEDS Liquids, does a really excellent job. And then Sean, Brian, and then the bottom, that's Mo and Nikhil. Next slide, please. I seem to have missed a slide. But so in the end, we're not yet done, but we're making really great progress towards our April 23rd test fire. If you're interested in looking at our code or electronics design, it's all open source at the SEDS-PSU GitHub organization. And we're really excited to be working on a literal rocket engine, and we hope to have a really successful test fire later this semester. Lastly, I'd love to chat about this. Is anyone who's curious? I'm in the FSW Slack. You could also email me or message me on Twitter. In the time that's left, I'm happy to answer any questions.
All right. Thank you, Lachlan. We do have some questions coming in. Looks like 5 so far, and we got some time to go through them.
Cool.
The first question is, cool project and additional respect for the bare metal Rust code.
Yes.
Is the sensor board pole-based or interrupt-based?
Say that again. Oh, is it pole-based or interrupt-based? It is interrupt-based. Everything is, actually, I can go in more depth about this. We're using this framework for Rust embedded on Cortex-M microcontrollers called RTIC, which stands for real-time interrupt-driven concurrency, I think. But basically, it's this way of having almost a threading system, so like a task system that's just based on these kind of timers and interrupts. And because of the way it's structured, it's actually guaranteed that you will not have deadlocks, which is a really nice characteristic to have. And so that means the whole thing is interrupt-based. We have tasks and stuff that are scheduled in the future that are just activated when we get a timer interrupt.
All right, wonderful. Next question from Jack White. The Cortex M4 is used in the discovery book. Was that the main motivation for its use? And how much did you use the standard M4 Cortex and ARM support crates? Did that present any problems with peripherals?
Yeah, so this one I think is an M3 processor. I've definitely read the Rust embedded book with the discovery book, and it's really excellent resource. We're mostly using the HAL crates for the STM32F1, but they're all very nice. And this project would not have been possible without the really excellent ecosystem built around embedded Rust on the Cortex-M devices.
All right, next question from Alan Cudmore. Do you have any thoughts on why Rust is gaining traction and enthusiastic users where languages like Ada did not?
Yeah, so I do have some thoughts about this, but I have to say at first that I've never used Ada. I think I've glanced at code written in Ada, but I've never used it or written it, so I can't really voice any opinions about Ada in of itself. I think Rust is gaining a lot of traction for a couple of reasons. One, that kind of broadly, not going into specifics about why this is, at least not right now, is that when you've written Rust code, it tends to work if it compiles, which is a very broad statement, kind of generalization. But in my experience, this honestly is true. If you write code and you structure it well and it compiles, it usually just works. And I don't know if that's the case with Ada. I know it's not the case, at least for me, with many other programming languages. And I think that is a significant reason why Rust is gaining traction. And it has a high learning curve, and there's a barrier to entry, which the Rust community has been working really hard to reduce. But once you use it and you get used to it, it's really hard to go back to anything else. It's just for that reason, and that is based on many other parts of Rust that all work together really well.
Okay, great. Next question. Good luck with the project. How is the data flow from sensors to the Raspberry Pi managed? Do the other two boards have some memory that is then forwarded every 10 milliseconds to the Raspberry Pi? Essentially, yeah. So we have for example, a sensor board has, I guess it's not really a global variable, might as well call it, which is essentially a big block of just, it's a big struct with like fields for the, each sensor has its own data, an integer in there essentially. And so that gets filled in over the 10 milliseconds between that the sensor board, reads data, and then the Raspberry Pi asks for the data, and the sensor board just sends that whole block over. Essentially, it gets serialized into a specific specific serialization format called postcard. What that is not really important, but it gets sent over and then deserialized on the other end. And that just gets sent over CAN. So it's just kind of very simple. There's really nothing too complex there. Okay. And next question, also from Alan Cudmore. Awesome project and presentation. Thank you. How do you manage safety for a rocket engine project? Do you have safety standards that you have to meet? That is a great question. And some of this is stuff that I'm responsible for, and then a lot of it is stuff that the other sub-teams of SEDS liquids are responsible for. For the electronics and the avionics part, a big part of the safety is just testing everything and trying to think of all the possible failure modes for things. What states could sensors be in? Could valves do weird things? All these different things. And so we have to take all of these into account when we write the code and design the electronics to make sure that we don't accidentally result in something going wrong during the fueling process, having a valve. Like, for example, having the nitrous oxide open when someone's standing next to it would be really bad. And so we have to be very careful about that. And also things like what I mentioned before, we have like a section of the output board kind of cordoned off so that it physically cannot like open the valves into the chamber or power the igniter unless a button like at the ground station is pressed physically. So you do all of that. You really have to be careful about safety. As for like safety procedures and stuff, that's definitely something I'm involved in, but I'm not a huge part of planning those. That's more like Matt, the lead of the SEDS liquids team. Okay, great. We've got a few more minutes left, but no other questions. So going to give just a bit, see if anybody filters in any other questions before we move on to the next item on the agenda.
Cool.
All right. Lachlan, thank you so much for your time
you.
this afternoon and sharing the great work from the SEDS team.
Thank you so much.